How's the volume level? Good? Okay. Thank you. Okay, my name is Gardner, and I've been working under Yvonne Smalyuk. And this presentation is entitled The Self-Spatial Organization and Self-Alignment of Fluorescent Nanoparticles in Their Crystals. So we're interested in using liquid crystals as this smart host to self-assemble nanoparticles. Now we're motivated, and we heard this earlier this morning also, motivated by self-assembly of metamaterials, and specifically metamaterials with negative refractive indices. Such metamaterials can be used for applications such as cloaking and super lenses. When I say super lenses, I mean lenses that are not diffraction limited. Other applications that may arise from the self-assembly of nanoparticles are optical circuits, which would provide larger data transfer rates, higher storage capacity, as well as miniaturization. And we just heard about liquid crystal lasing, liquid crystal mirrorless lasing, and I want to come back to that a little bit later in my presentation. So our goal is to use fluorescent nanoparticles to study the interactions and self-assembly of nanoparticles in liquid crystal. Now we're using cadmium selenite fluorescent nanoparticles. We're using fluorescent nanoparticles so we can image them using polarization-sensitive confocal microscopy. So these cadmium selenite nanoparticles emit strong and non-bleaching polarization-sensitive fluorescence. They were synthesized by our collaborators at SUNY Buffalo, and here are two images that I took from their paper. So here's an image showing the nanorods. So available to us, let me mention that first, are nanospheres of about 8 nanometer diameters, nanorods, and nanomultipods. So this image shows some of these nanorods, and over here also in this cartoon. So these nanorods have controlled diameters between 4 and 8 nanometers, and then controlled lengths between 30 and 50 nanometers. And these are nano-dispersed nanoparticles. So, depending on how they're synthesized, they can control these lengths. And in this image here are some of the nanomultipods. And here they're actually tripods. So we can imagine immersing some of these nanoparticles in a liquid crystal, specifically a uniform director field. So shown here is a nanosphere immersed in a uniform far-field director, and we see this quadrupole distortion. And then down here is the nanorod immersed in, again, a uniform far-field director. And again, we see distortions. So, to minimize elastic free energy costs, these particles can do one of two things, and or both of these. They can phase separate to the surfaces, to the substrates, or they can interact with each other to form complex structures to minimize the elastic free energy. But before that, let's just start by looking at these nanoparticles in the isotropic phase of a pneumatic liquid crystal. And this video will show the trend. So let's see, it's not that bright in here, but what we see is that these nanoparticles are uniformly dispersed because there is no elastic free energy cost. And they undergo Brownian motion. So here we can see some blinking of some of these particles, and that's because they're going in and out of the focal plane. And let me just mention that we can detect fluorescence from individual dispersed nanoparticles with our fluorescent confocal microscope. But now, so if we start in the isotropic phase with uniformly dispersed nanoparticles and then cool into the pneumatic phase, this is what we see. So this is just a little movie of some clips. So showing blue is the pneumatic phase, and then in black is the isotropic phase. And let me just highlight one particle as it starts. It starts right here. So in order for it to minimize free energy distortions, this particle will remain in the isotropic phase as long as possible, so it kind of moves down until it's completely enveloped by the crystal. And what we also notice when we quench into the pneumatic phase is that these particles phase separated. So in this image up here, it's a vertical confocal cross-section of our sample looking down into our sample. And what we see is we see the strong fluorescence from the nanoparticles from our substrate. So there's one here and there's also one down there, but again, some of these aren't coming up so great. But we do see the space separation. It's also depicted in these cartoons here, both in the planar alignment and the homeotropic alignment. We do see the space separation, so I try to draw these nanospheres in the liquid crystal phase. That's space separated. And then let's talk about defects real quick in liquid crystals. So of course there's high energy, high elastic free energy costs associated with these defects, and the defect cores usually melt into the isotropic phase. So I try to illustrate by drawing these little red circles around the defect core. So as we've seen, the nanoparticles like to remain in the isotropic phase. So we hypothesize, there we go, for two reasons that these nanoparticles will tend to assemble in these defect cores. So first of all, if they're in the defect core, it's going to reduce the elastic distortions around the particle. And secondly, these nanoparticles will occupy some of the energetically costly volume at the defect core. So for these two reasons, we should see the self-assembly of these nanoparticles in defect cores. And these are two images showing exactly this. So in this top image, we have this displanation line to our sample, and it comes around here and kind of loops back. And we see the fluorescence from the nanoparticles along this displanation line, and also here. And these are two clips from a movie. So in this movie, this displanation line was contracting, shrinking, and these nanoparticles remained aligned along the displanation line as it contracted. So it's definitely showing that they are in the displanation core and remain there. But for the applications that I mentioned by our motivations, usually we need this like periodic arrangement of nanoparticles. And to accomplish this, we're interested in like liquid crystal phases that show periodic defect patterns. One such phase is the twist gain boundary phase, and then in this phase, symmetric blocks are separated by 100 nanometers or less by these screw dislocations. And that's one such phase. And another such phase with these periodic defect patterns is the blue phase, which we heard about earlier, so I won't go too much into it. I just we heard about the double twist cylinder, in which the cholesteric molecules, so the central molecule will align along the cylindrical axis, and then radially outward, they will twist out in all directions, and it'll give rise to this double twist cylinder. And then this double twist cylinder will form these cubic lattices. And also was mentioned earlier that there's these displanation lines throughout the cubic lattice, and with these defect cores. So one might expect that these nanoparticles in here, and now I'm using nanorods, will go to these displanation cores. Or these displanation lines. So here I'm trying to animate them, self-assembling into the displanations. There we go, there's 12 of them. Okay. Before we get into some of the images I took of these nanoparticles self-assembling into these displanation lines, let's look at what happens when there is no nanoparticles in the cholesteric liquid crystal. So in the sample I was working with, it was isotropic around 7 degrees Celsius. And then I'm cooling, and over about 1 degree Celsius, I witnessed the blue phases. And then as I cool down to room temperature, without any nanorods, I see the cholesteric phase with this oily streak texture. But if I mix some nanorods in my cholesteric sample, in the isotropic phase, I mix in the nanorods, and then I sonicate it to get some heat, to make sure that they're uniformly dispersed, and then cool, what I see is domains of blue phase that were stable down to room temperature. And we identify these blue phase domains based upon their characteristic selective reflection of light. So let me do a little compare and contrast here with and without nanoparticles. So these are two cross-polarized microscopy images. So with the nanoparticles, we see this blue phase domain coexisting with the cholesteric phase around it. So you can see the oily streak texture around the blue phase domain, and we see this blue phase domain. And maybe here in the bottom corner, it says approximately 0.15% nanoparticles to liquid crystal by weight. And without any nanoparticles, we just see the oily streaks in the cholesteric. And these are both at room temperature with that sample that was isotropic at 70 degrees. So here are fluorescent confocal images that I took. So this top one here is showing the fluorescence from the nanoparticles is confined to these blue phase domains in our sample. And this is an XY confocal scan. And then this image over here is corresponds to this image right here with the confocal microscope. And in case you can't see in the back, it's kind of small. So this says 50 microns and 50 microns is the size of these scales. And so then I did a vertical cross-section along the horizontal to look at the nanoparticles and how they're dispersed throughout the sample. And what I see here, and it's again not coming out so well, but they are self-spatially organized in the bulk. So we're not limited by just phase separation of these nanoparticles. We actually self-assemble them also in the bulk. And then I did a diagonal here, which I labeled B, and here's a vertical cross-section B, and that didn't come out at all. But trust me, it's there on my computer. It's bright. So I wanted to show some more images. This will be clear. This will come out. I know it will. It's a video of me doing some going through my sample, doing optical slicing through my sample. And as I go through my sample, what I see is these fluorescent domains of these nanoparticles in the blue phase at different depths in my sample. And my sample depth here is about 35 microns throughout my sample. And we do half micron steps optical slicing through this. So, and then I try to also show that with these vertical cross sections over here. That there's some blue phase domains near the top substrate, some in the bulk, and then some near the bottom. These could be used for applications because we have this periodic arrangement of these nanoparticles, such as we heard earlier, this lasing. And one direct application of using fluorescent nanoparticles is that these fluorescent nanoparticles do not bleach. So that would be a big benefit for these liquid crystal lasing. And by studying the fluorescent nanoparticles, we hope to generalize and then we can do self-assembly of various compositions of nanoparticles such as silver, gold, magnetic, nanowires, and these kind of particles could be used for the self-assembly fabrication of metamaterials. Such metamaterials as invisibility, which was recently demonstrated, and I guess so. One of the problems from going from this was demonstrated at microwave frequency. So one of the problems going from microwave to visible wavelengths is we got to go from the millimeter scale of fabrication of these metamaterials into the nanometer scale. So again, these are some of the motivating factors. So let me start to conclude here. The minimization of free energy and defects allows for the self-spatial organization and self-alignment of nanoparticles. And by using liquid crystals that have periodic defect patterns, we can arrange these nanoparticles in periodic arrays. And these can be used for applications such as lasing and possibly also fabrication of metamaterials at optical wavelengths. Let me give special thanks to the SMART program at the University of Colorado Boulder, and thank you, everybody.
Great. Questions for Dennis?
Do you get any higher concentration of blue phases if you increase the concentration of nanoparticles?
Good point, and that's what I want to look into. That's honestly, maybe I can give blue phase throughout my sample. And yeah, I want to increase concentration. So that's something that I want to do when I get back to work in the lab. Definitely.
Anybody else?
The nanoparticle treated with something maybe fluorescent or by itself is fluorescent?
It's fluorescent by itself. The cadmium cellulite is fluorescent by itself. Yeah, we haven't treated it by any.
Was your regions of blue phase mobile? Could they move around within the Cholesteric? Could they coalesce with other domains?
No, I didn't see it, and I mean they were stable for I mean, they're still stable in the sample, just like they are now. So I haven't seen them move around or interact with each other. They're kind of separated. And I think it's because of my relatively kind of low concentrations that there just isn't enough nanoparticles to stabilize multiple phases of domains of blue phase.
Are you using surfactants to get the particles in?
No. I'm not treating the glass either. It's just
I mean, for the blue phase and the fluorescent phase, what it takes, do you see nanoparticle in fluorescent phase?
yes, I see very little fluorescence coming from the rest in the cholesteric phase. There is some sort of uniform dispersed nanoparticles throughout the cholesteric. Because I think some of them don't recognize or can't assemble into this blue phase, so they're kind of spread out.
Do you have any idea? Is it stabilized by rods as well as by spheres?
I have done it with rods and not spheres yet. And in our setup, we had trouble with one of our lasers, so and we couldn't excite the spheres as well. So I switched to rods and been working with rods lately until we get some more lasers to excite the spheres. They get excited at just slightly different wavelengths.
So do you have any idea what the quantum efficiency of those? What is the actual quantum efficiency of the reports?
It's very high, but indeed, do you remember?
No, I don't remember, and I would refer. I mean, everything I know about these nanoparticle halls, all in the beginning, is from the paper by our collaborators at Sunny Buffalo. I'm trying to show that from them. So I don't remember.
Okay, let's thank Dennis and all speakers this morning. Ivan has an announcement.
So today we have a lunch on the University Hill. We want you to try not only just sandwiches in Boulder. We have wonderful restaurants, and today we will show you how to get to some of those which are next to the university, and later on for dinner we will go to the Pearl Street region of Boulder, where again we will have many wonderful opportunities to have really excellent dinner. So right now there will be